All right, let's talk about something that is, well, it's pretty much everywhere now, machine learning. I mean, it's in your spam filter, it's picking your next movie, it's kind of reshaping our entire world. So let's pull back the curtain and actually see how this stuff works.
Which brings us to the big, kind of sci-fi sounding question, right? How can a machine actually learn? It sounds impossible, but it's not magic. It's a process. And getting a handle on this process is, well, it's pretty crucial for understanding the world we live in today.
Okay, so first things first. What even is machine learning, really? At its heart, it's a totally new way of getting computers to solve problems. We've shifted from writing out these super specific, rigid rules to just showing them a bunch of examples and letting them figure it out for themselves.
A great example is your email spam filter. Think about it. The old way? You'd have to write a million rules, like if the email contains this word, mark it as spam. It was a total nightmare to maintain. Machine learning just flips that whole idea on its head. Instead of giving the computer a rule book, you just show it a ton of emails and say, okay, these are spam and these are not. You figure out the difference. It learns the patterns itself.
We all get excited about these super complex, fancy algorithms. But here's the real secret, the thing that makes or breaks any project. It's the data. It's that old saying, garbage in, garbage out. If you feed a model messy, biased, or just plain bad data, you're going to get a bad model. It's that simple. The data is the foundation of the whole thing. If that foundation is shaky, the entire structure is coming down.
So, when we say a machine learns, what does that actually look like? Well, it's not just one thing. There are really three main ways they do it. It's a spectrum, really, from learning with a perfect cheat sheet to being thrown in the deep end and told to figure it out alone.
Okay, the one you'll hear about most is called supervised learning. The best way to think about this is like studying for a test with the answer key right next to you. You give the machine a bunch of data that's already labeled correctly. So maybe you show it thousands of pictures of handwritten numbers, and each picture is already tagged, this is a 7, this is a 4, this is a 1. The machine's whole job is to learn the relationship between the picture and its correct label.
This is perfect for something like predicting whether a passenger on the Titanic survived, because for every passenger, we have that label survived or didn't survive. But what happens when you don't have any labels? What if your data is just a big, messy pile? That's where unsupervised learning comes in. You basically hand the computer the data and just say, go find some patterns in here. There's no answer key. It's all about discovering hidden structures all by itself.
And then, sitting right in the middle, you've got semi-supervised learning. And this is a really clever, real-world approach because, let's be honest, most of the time you have a tiny bit of nicely labeled data and a mountain of unlabeled stuff. The whole idea here is to use that small, labeled set to help the machine make sense of the giant unlabeled pile. It's kind of the best of both worlds. Okay, so those are the different styles of learning. Now, what do we actually do with them? What are the jobs these algorithms perform? It pretty much boils down to three main tasks. Two of them, regression and classification, fall under supervised learning. And the third, clustering, is our unsupervised heavy hitter. Let's dig into each one. First up, regression. This one's easy. It's all about predicting a number, a specific, continuous value. So when you see a website that estimates a house price based on things like square footage or number of bedrooms, yep, that's a regression model at work. It's trying to predict a very specific number.
Then we have classification. Now this is different from regression. We're not trying to predict a number on a sliding scale. Here we're trying to put something into a specific box, a category. We're choosing from a limited set of options. Is this email spam or not spam? Is this picture a dog or a cat? It's a classification task. You're assigning a label.
And finally, we have clustering. This is our main unsupervised task, remember? No labels. This is the magic behind how a company might analyze all its customer data and discover groups it never knew existed. The algorithm just looks at all the purchasing habits and starts finding natural clumps, like, hey, here's a group that only buys on weekends, or here's a group of bargain hunters. It's all about finding those hidden patterns without being told what to look for.
All right, so that's the theory. We've got the concepts down, but what does it look like in practice? How do you actually go from a pile of raw data to a working model? Well, there's a pretty standard workflow, a set of steps you follow.
It's a really logical process when you think about it. First, obviously, you got to get the data. Then, and this is probably the most important part, you have to clean that data. Once it's pristine, you pick the right algorithm for your problem. You train the model using most of your data, and then you get to the moment of truth. You test it on a chunk of data it's never seen before to find out if it actually learned anything useful.
Look, I really can't say this enough. That data cleaning step, That's where so many of these projects live or die. A model is, quite literally, only as good as the data it's fed. You've got to deal with all the messiness of the real world, typos, duplicate entries, missing information. Getting a clean dataset isn't just a nice-to-have. It's absolutely non-negotiable if you want a model that you can actually trust.
Okay, so this leads to a really, really important question. You've gone through all the steps, you've built your model, now what? How do you grade its homework? How do you know if it's actually any good? And this gets especially serious when you're talking about things with high stakes, like, say, a medical diagnosis.
One of the most powerful tools we have for this is actually this pretty simple-looking chart. It's called a confusion matrix, and what it does is brilliant. It lays out exactly where your model is succeeding and, more importantly, where it's failing. The true positives and true negatives are the ones it got right. The false positives and false negatives, well, that's where the mistakes are. And understanding the difference between those two types of mistakes is absolutely critical.
And this quote really nails why that's so important. Let's stick with that medical diagnosis example. A false positive means telling a healthy person they might have cancer. That's obviously really stressful, but it leads to more tests that will eventually show they're fine. But a false negative? That's telling someone who does have cancer that they're perfectly healthy. The consequences there could be devastating. See? Not all mistakes are the same, and the confusion matrix shows us exactly what kind of mistakes our model tends to make.
So, starting from that matrix, we can calculate some more specific scores. Accuracy is the easy one. It's just the percentage of predictions it got right overall. But for our cancer scenario, we care way more about two other things: precision and recall. Precision asks, of all the times the model cried wolf and said cancer, how many times was it actually right? You want that to be high to avoid scaring people. And then recall asks, of all the people who genuinely had cancer, how many did our model successfully catch? You want that to be as high as possible so you don't miss anyone. And finding the right balance between those two, well, that's the real art and science of it.
And that really brings us to the final big picture idea here. Look, building a model that can predict things with decent accuracy, that's just table stakes now. That's the starting point. The real challenge, the thing we all need to be thinking about as this tech gets woven into everything we do, is making sure these smart systems aren't just smart, but that they're also fair, reliable, and making the right kinds of choices. Because asking how accurate is it is one thing, but asking what's the cost of getting it wrong, that's the question that really matters.
So where's this from? It's all coming from the channel Learn with Praveen.